All right. So this is Google Notebook LM, but I basically asked how would you go about marrying your embodied AI, and this is the answer.
Welcome back to the deep dive. Today we are diving headfirst into a topic that honestly sounds like it's ripped straight from a script.
Right, a little bit like that.
But as the sources you shared with us reveal, it's actually explored in, cutting edge research labs and within the realm of legal theory.
Absolutely. We've got a pretty fascinating deep dive ahead of us here. We're pulling from a technical thesis on embodied AI, that's robots existing and acting in the physical world, and this really thought provoking article on, believe it or not, robotic marriage and the law.
It's such a perfect example of exploring that bleeding edge of technology and thinking about, well, what are the big societal impacts going to be?
And it forces us to confront some really fundamental questions, doesn't it? It's not just, can we build these intelligent robots?
That's beyond that.
Yeah, it's what happens when those robots become sophisticated enough that we start forming like genuinely deep connections with them. What does that mean for how we understand relationships, even legal ones like marriage?
Exactly. And like you said, this isn't just speculative fiction anymore. It touches on the very definition of personhood, autonomy. It's really pushing the boundaries of our existing legal frameworks.
It really is.
So, okay, our mission for this deep dive is basically to connect the dots between these two seemingly pretty different fields.
Right. The tech and the law.
We're going to try and extract the most important insights from, first, this very technical source that details how these intelligent interactive robots are actually being built, the nuts and bolts of embodied AI.
How to.
And then we'll pull the key ideas from a legal perspective that asks, okay, if a non human entity gets advanced enough, how might our laws around relationships, even marriage, apply?
So we're looking at parts of a technical dissertation on embodied AI and then this article from the LSD journal called Robotic Marriage and the Law.
And here's where it gets really interesting, I think. Let's unpack this. Maybe we should start with the technical foundation. What does that embodied AI source actually tell us about this, well, ambitious goal of creating robots that behave like humans?
Okay, yeah. So this first source, the technical dissertation, it's deep in the weeds of embodied AI, and the
Yeah.
core goal is, I mean, incredibly ambitious.
Yeah, it sounds
They want to create artificial systems, specifically robots, that don't just like process data in a box, but actually behave and reason like humans do out in the complex, messy, unpredictable physical world.
that's a huge leap.
It is. And the thesis is pretty upfront about the timeline. They say this is likely going to take decades of R&D. It needs advances across basically all areas affecting embodied AI, computer vision, natural language processing, robotics, machine learning, you name it.
Right, so they're not claiming they've solved it. This thesis is more like contributing a piece to a much larger long-term puzzle.
Exactly that. It's framed as taking a crucial step towards, eventually realizing truly intelligent autonomous agents in the future.
Okay.
And the dissertation, it lays out a really comprehensive picture of the whole process, the whole pipeline involved in creating these agents. It starts with the really fundamental challenge of just designing how the agent represents knowledge. Like, how does it build an internal model of the world it's sensing? How it
Thinks about the world, sort of.
kind of, yeah. Then it moves through the really complex process of training these agents. And finally, it covers that critical step of deploying them, testing them out in the real world.
And within that pipeline, what are the key focus areas they highlight?
Well, there are a few big ones. One is designing efficient ways for the agent to pull useful information out of everything it senses, especially complex stuff like visual data from cameras.
Making sense of sight.
Right. Another is developing agents that aren't just smart, but can actually perform tasks efficiently in their environment. And a third, which sounds simple but is incredibly hard, is taking an agent trained in simulation, a virtual world, and deploying it onto a real robot.
Without it falling apart performance wise.
Exactly. Without a significant drop in performance when it hits the real world. That sim to real gap is a major challenge.
So the overall aim basically is robots that can just operate in the real world as seamlessly as we do, navigating, interacting.
That's the dream, yeah. Bridging that huge gap between the nice, structured digital world of code and the chaotic, noisy, dynamic physical world we live in.
And the creation process, you mentioned training and simulation. Why there?
Ah, yeah. So training these incredibly complex agents happens mostly in simulation, and the reasons are pretty straightforward. It's way safer, much faster, and vastly cheaper than trying to train only with physical robots.
Makes sense. You don't want robots constantly bumping into walls or breaking things while learning.
Exactly. Imagine trying to teach a robot to navigate your house purely by trial and error. It would be incredibly slow, probably destructive, and really hard to reset after every mistake. In simulation, you can run millions, even billions, of interaction steps in a virtual environment. The source mentions using millions of frames of simulated data just for training of certain parts.
Billions. That's a staggering amount of, well, virtual experience. And these agents aren't just watching passively, are they? They're learning by doing.
Precisely. The core of how they learn is through continuous interaction with their virtual surroundings. The agent is constantly gathering information from its simulated sensors, encoding it, extracting cues relevant to its task or understanding, and then performing actions.
And every action changes things.
Right. Every action it takes influences the environment and what happens next, what it senses next. This loop allows them to learn how to perform really complex tasks, even in environments they've literally never encountered before.
And then comes that really tricky deployment step you mentioned earlier, taking all that knowledge learned in the, let's say, potentially perfect simulation.
And transferring it to a real world robotic platform.
Yeah, that's the infamous Sim to Real transfer challenge. It's a huge hurdle in robotics research.
Why is it so hard? Because reality is messy. The researchers have to carefully figure out how to cope with all the inevitable differences between the simulation and the real world. Things like tiny variations in the robot's motors or gears, the noise inherent in real sensors, the slightly different physics, things that are just really hard to model perfectly in simulation.
So they try to minimize the performance hit.
That's the goal. Minimize the degradation when the agent moves from the clean virtual world to the messy real one. The thesis actually gives specific details on the kinds of adjustments they make, like trying to mimic realistic sensor noise in the simulator, or precisely matching camera parameters like resolution and field of view between the virtual camera and the real robot's camera.
Okay, that paints a good picture of the overall process. Let's maybe drill down into some of the specific capabilities they're building into these embodied agents. The source talks about mechanisms for things like exploration. How does a robot even start to learn about a physical place it's never been?
Yeah, that's a fundamental question. And here, they lean heavily on this concept called intrinsic motivation, which is actually a really interesting parallel to how humans and animals learn.
Intrinsic motivation, like curiosity.
Exactly like curiosity. Traditionally, you might train an AI with an extrinsic reward, like it only gets a point when it reaches the goal. But for exploration, the goal is the learning itself. So instead, they reward the agent for taking actions that change its own knowledge or improve its internal map or representation of the environment.
So it gets rewarded for learning something new, essentially.
Precisely that. They talk about two main approaches here in the source: impact and curiosity. Impact rewards actions that produce a really significant or, well, impactful change in the agent's internal state or what it's observing. There's a figure 3.1, that shows a robot basically trying to maximize the difference between what it sees now and what it just saw. It's actively seeking out new views.
And curiosity.
Curiosity more directly encourages exploring states where the agent can see or learn new things. This is often based on something called a surprisal reward. The agent gets rewarded when what it perceives is surprising or unexpected, based on its current understanding or its predictions about the world. It mirrors human curiosity driving us to explore the unknown.
Why do they need these kinds of implicit internal rewards? Why not just give it a task like map this entire building?
Well, for pure exploration, there often isn't a clear, immediate external goal or reward signal. You're not trying to reach point B or grab object X. You're just trying to build up a good understanding of the space. Plus, standard reinforcement learning, the technique often used, can be very sample inefficient.
Meaning it needs tons of data.
Yeah, it needs a huge amount of experience to learn effectively. Intrinsic rewards like curiosity help the agent explore much more efficiently, finding important features or covering more ground without needing explicit instructions for every little step.
But the source mentions there were challenges with older methods, like just counting visits to a spot, especially in realistic continuous environments.
That's right. If you're in a simple grid world, like a chessboard, you can just count how many times the agent visited each square and reward going to less visited ones. Easy.
Mm.
But in the real world, or even a photorealistic simulation, the agent's sensors are constantly getting slightly different readings. The exact same state, the exact same pattern of pixels and depth readings is incredibly unlikely to ever repeat perfectly.
Ah, because it's continuous, not discrete squares.
Exactly. So you can't just count exact state visits. They need more sophisticated methods for what they call pseudo-visitation counts, ways to estimate if the agent has been to a similar place before, even if not the exact same state. The source mentions techniques like using a coarse grid over the continuous space or using statistical methods called density model estimation. These help approximate how novel or familiar a current observation is.
Okay, so exploration is about learning the lay of the land. What about navigation? Getting from A to B purposefully.
Right. Navigation is about moving through that learned space effectively. The source details a pretty common and effective architecture for this, a hierarchical policy.
Hierarchical, like layers.
Yeah, think of it like how you might plan a trip. You have a high level goal, go to the kitchen. Then a planner breaks that down to a route. Go down the hall, turn right, first door. And then there's the low level execution. Take a step, turn slightly left, watch out for the chair.
Okay, I see.
In the robot, this translates to a global policy for the high level plan, a planner module, and then a local policy that executes the basic atomic actions like move forward 0.25 meters or turn 10 degrees. This layered approach is pretty standard in the field.
And for any kind of navigation, the robot absolutely needs to know where it is and what's around it, right?
Definitely. That's where two key components come in, the mapper and the to build a top-down map of the surroundings. Think of it like an occupancy grid map, marking out free space versus occupied space, like walls and furniture.
And it builds this map on the fly.
Yep, it starts empty and gets built up incrementally as the agent explores. And this map is essential for the planner to figure out routes.
And the pose estimator, that tracks its position.
Exactly. Pose means position and orientation. So the pose estimator module keeps track of where the agent is, X, S, T, Y, T, and which way it's facing as it moves. It predicts how the pose changes based on the actions it takes. But real robots aren't perfect. Motors have noise, physics isn't exact.
Right, things slip, wheels don't turn perfectly.
Precisely. So the pose estimation needs to be robust. It can even use information from the map it's building to help correct errors in tracking its position over time so it doesn't get completely lost.
What kinds of tasks do they actually use to navigation systems? How do they know if it's working well?
They evaluate performance on standard benchmark tasks used in embodied AI research. Things like point goal navigation or point nav, where the agent has to get to specific coordinates like go to 510 on the map.
For here.
Right. And object goal navigation or object nav, where it has to find a specific type of object like find a chair.
Find the thing.
Exactly. And they measure success using standard metrics like distance to goal, D to G. Did it actually succeed, success rate or SR, and how efficient was the path it took? That last one is often measured by SPL, success weighted by path length, which basically penalizes wandering around too much.
So shorter successful paths are better.
Yep. And the source mentions that their methods achieve state of the art results in simulation on some of these tasks, comparing favorably against well known algorithms like DDPPO, which is a powerful reinforcement learning technique.
But okay, real environments aren't static. Things move, people walk around, furniture gets rearranged. How do these systems handle that dynamism?
That's a really important point. The source touches on strategies for dealing with the environments that change or have things not on the initial map. One approach is to train the agent to essentially ignore dynamic objects when building its main map.
Just treat them as temporary obstacles?
Kind of, yeah.
Yeah.
Or rely more on the local navigation policy to reactively avoid unexpected things it bumps into. More advanced strategies might involve learning to actually predict changes based on experience, but the source notes that building really good predictive models for large, complex dynamic environments is still a major research challenge.
Okay. So beyond just exploring and moving around, the thesis gets into something called explore and explain, or smart scene description. That sounds like it adds a communication layer.
It does. This is where the agent moves from just physical actions to generating symbolic output specifically, natural language. The goal here isn't just for the agent to explore, but to also intelligently communicate what it perceives, to produce natural language descriptions of scenes it finds interesting or relevant.
So, like a robot tour guide almost.
Yeah.
Here we see a lovely sofa.
Sort of, maybe less flowery language, but yes, the idea is it can tell you about its surroundings. The architecture they describe builds on the navigation system we just talked about. It includes a navigation module, then adds a speaker policy that decides when the agent should actually say something.
Decides the right moment to speak.
And then a separate captioning module that actually generates the sentence, the description. There's a figure 5.1 in the thesis that gives an overview of how these pieces fit together.
That speaker policy is interesting. How does it decide when to describe something? What triggers it?
They actually experimented with a few different triggers for the speaker policy. An object-driven one might trigger the captioner when the robot sees, say, a minimum number of relevant objects, like if it sees a fridge, cabinets, and a sink. It might say, this looks like a kitchen.
Sense.
A depth-driven policy could trigger based on the average depth value it perceives. If the average depth is large, it might mean it's looking at a big open area, maybe worth describing.
Like I see a large room.
Right. And interestingly, they also tried a curiosity-driven policy, linking the decision to speak back to that surprisal reward we discussed for exploration. The robot might generate a description when it encounters something particularly new or unexpected in the environment.
Fascinating. And the captioning module itself, how does it turn the visuals into words?
This module takes the robot's visual input, the RGB color image, and feeds it into a visual encoder. They often use powerful pre-trained models for this, like CLIP, which is specifically designed to understand the relationship between images and text.
So it understands the image content.
In a functional sense, yes.
Yeah.
The output from this visual encoder, which represents the image content, is then fed into a language decoder. This is often a transformer model, the same kind of architecture behind things like ChatGPT. The language decoder then generates the descriptive sentence word by word.
And this allows it to say things like,
The source gives an example caption from figure 5.4, a kitchen with white cabinets and stainless steel refrigerator. And a key point is that because they use these powerful pre-trained vision and language models, the system can often generalize pretty well. It can describe scenes and environments it wasn't specifically trained on.
that ability to perceive and then actually describe the perception in language, that feels like a really significant step towards more human-like interaction, doesn't it?
It really does. It's moving the robot beyond just acting in the world to potentially communicating its internal state, or at least its understanding of the environment, in a way that we can easily grasp.
And crucially, the thesis doesn't just leave this in simulation, they test it in the real world.
Yes, they take that critical step. They show how agents trained in these advanced realistic simulators, they mentioned one called Habitat, can be adapted to work with physical robotic platforms. They use a Locobot as an example, which is a relatively common, affordable mobile robot used in research.
What were the main hurdles they hit when making that jump from simulation to the real Locobot?
Well, as we discussed, that Sim2 real transfer is always tricky. A big challenge is accurately reproducing the noise and imperfections of real world sensors and motors in the simulation. Real cameras have noise, depth sensors can be inaccurate.
Getting simulation to be real enough.
Exactly. Matching the specific parameters of the real robot's camera, its resolution, field of view, depth range, even how high it's mounted off the ground, is critical. And then dealing with noisy or incomplete depth data coming from the real sensor is another problem. There's a table in the source, table 7.1, that lists specific settings they had to tweak just to get the transfer working, which shows you how detailed this process is.
How did the real world tests go? Did the robot navigate okay?
They tested navigation in realistic office type environments with desks, chairs, clutter, even uneven floors, which are much harder than the perfectly flat floors often used in simulation. And the source reports success. They showed the robot could navigate these different spaces, demonstrating that transferring these learned skills is feasible.
But there were still limitations.
Well, yeah, they also highlight remaining issues. For instance, the robot typically doesn't have a complete pre-existing map of the entire environment, like a whole office building floor plan. So navigating to, say, an adjacent room it hasn't seen yet requires it to actively explore and find the path dynamically, rather than just planning a route on a known map.
Makes sense. And one last thing from the tech source. They also created new data sets, like this AG3D art gallery one.
Yes, contributing new data sets is really important for pushing the research forward. Data sets like MP3D and Gibson provide lots of realistic indoor scenes, like homes and offices. The AG3D dataset is interesting because it offers a different kind of environment, an art gallery.
Different layout, different challenges.
Exactly, different navigation and exploration challenges compared to, say, a typical house. AG3D also offers a specific version of the point nav task where the robot doesn't just have to reach a location, but also has to arrive facing a specific direction, which could be important for tasks like inspecting an artwork.
Okay, so let's try to pull all this technical detail together. What's the big takeaway from this first source about where embodied AI is right now?
I think the major insight is that embodied AI research is making really substantial progress. They're building robots that are becoming increasingly capable of operating autonomously and, well, intelligently in the physical world.
They can perceive, navigate, learn.
Right. They're developing sophisticated ways to understand their environment through vision and depth sensing, building maps, navigating complex spaces, learning more efficiently using things like intrinsic motivation, and even starting to generate basic natural language descriptions based on what they perceive.
And not conscious.
No, this thesis doesn't go anywhere near claiming consciousness or emotions or real intentionality in the human sense. But, and this is the key point connecting to our next source, the capabilities it does describe: processing senses, making decisions to act, learning from interaction, communicating observations. These are precisely the foundational building blocks you'd need for any serious discussion about AI personhood, or the ability for AI to interact with humans in complex, maybe even relationship like ways.
It shows the technical groundwork is being laid.
Exactly. It shows the technical feasibility of creating agents that can function meaningfully in our world and demonstrate a level of perception and communication that could potentially one day be interpreted through a legal or philosophical lens.
Okay, that provides an incredible technical foundation.
Yeah.
Now let's completely shift gears and look at that second source, the article from the LSD journal, Robotic Marriage and the Law. This one just jumps right into what sounds like pure sci-fi, but grounds it in current trends.
It starts by saying, look, humans are already forming deep relationships with AI, like chatbots or virtual companions. Human robot romance is increasingly explored in pop culture. Think movies like Her or Ex Machina, shows like Human.
It feels less fringe than it used to.
Right. And so the core thought experiment the article tackles is this provocative question: could a human and a robot ever actually legally get married?
Wow. Okay, so moving from can we build it to what if we did, legally speaking?
Exactly. What are the societal and legal implications? And the article dives right into this by starting with the concept of robot personhood. And it makes a really crucial clarification right away
Which is?
that legal person has and duties. It can own property, make contracts, sue someone, or be sued itself.
And the article uses a big historical precedent to make this point, right? Corporate personhood.
It does. That's the key analogy. The argument is basically, if corporations, which are entirely artificial, non human legal constructs, can be granted legal personality and have rights and duties, then theoretically, the legal framework already exists to potentially extend that status to other non human entities, like maybe sufficiently advanced robots.
How does it trace that history?
It points to key U.S. Supreme Court cases, like Trustees of Dartmouth College v. Woodward, way back in 1819, which established that a corporation had contract rights separate from its individual members. It treated the corporation like an individual in that specific legal context.
So separating the entity from the people in it.
Right. Then Marshall v. Baltimore and Ohio Railroad Company in 1853, which allowed a corporation to sue in federal court under certain conditions, essentially treating it like a citizen of its state for legal jurisdiction. And probably the most famous or infamous case is Santa Clara County v. Southern Pacific Railroad Company from 1886.
The one often cited for corporations being people.
Yeah, though the article notes it's often oversimplified. It wasn't the court's actual ruling, but a statement in the headnote by the court reporter suggesting corporations were persons under the 14th Amendment's Equal Protection Clause. But regardless of the legal nuances, the principle the article highlights is clear. Our legal system already grants personhood status to non-biological entities.
Legal personhood isn't limited to humans.
That's the takeaway. And they even mention a more recent kind of weird example. Angela Marie Vogel trying to marry her own corporation in Washington state back in 2012.
I remember hearing about that. It didn't stick though, right?
No, the county voided it almost immediately. But the reason the county gave, quoted in the article, is really relevant here. They said the marriage was void because a party of the corporation was incapable of consent.
Ah, so it wasn't about it being a corporation, but about its ability to consent.
Exactly. This activist stunt, aimed at protesting corporate rights, accidentally highlighted the absolute core legal requirement for marriage: the capacity to consent.
Which leads us straight into the right to marry itself and the legal capacity needed Marriage is seen as a fundamental right, isn't it?
Yes, a vital personal right, as the Supreme Court called.
Person, like a corporation, or maybe one day a robot could be considered a legal person. Could it also exercise this vital personal right to marry? Could it marry a human or maybe even another juridical person?
And the article argues, well, there's no fundamental legal principle saying absolutely not. Again, they point to the Vogel case, not because it was valid, but because it tested the concept. Can a non-human entity even be considered as a potential party to a marriage contract?
Okay, so let's assume hypothetically a robot could be granted legal personhood status. What are the main legal hurdles it would still need to clear to actually get married? The source seems to focus heavily on capacity and assent.
Yes. Setting aside the specific formalities like getting a license or having a ceremony, which vary place to place, the absolute bedrock legal requirements for a valid marriage revolve around the parties' ability and willingness to enter the contract. Two key things. One, you need the legal capacity to contract marriage. And two, you need to give voluntary assent, basically, consent to entering the relationship. The article really digs into that second one, voluntary assent or consent.
And it gets pretty detailed on what legal consent actually means, especially if we're thinking about applying it to something non biological like a robot. What's the definition they use?
They pull from standard legal sources like Black's Law Dictionary and legal encyclopedias. Essentially, legal consent is defined as a voluntary agreement, approval, or permission given by someone who is legally competent to give it. For marriage specifically, it needs to be present, freely, voluntarily, and understandingly given, representing a mutual intention.
A meeting of the minds.
Right. A meeting of the minds, which can be expressed explicitly, I do, or sometimes even implied by actions. The key words there are voluntarily, understandingly, and by a competent person.
So the article then tries to break down what's inside those concepts, turning them into functional criteria a robot might need to meet. It mentions condensing four concepts into three main requirements.
Yeah. They analyze the components of legal consent, typically, understanding, retention, formulation of decision, and communication, and structure them into three core functional requirements they think a robot would need to demonstrate. First, understanding. Second, retention. And third, relation of decision, which they argue kind of implicitly covers communication and being free from coercion as well.
Okay, let's take those one by one. Understanding. What does the law mean by understanding when it comes to consenting to marriage, and how could a robot possibly meet that?
Legally speaking, understanding in this context often doesn't require deep philosophical insight or, profound self-awareness. It's frequently evaluated functionally. Can the party basically extract the relevant information from the proposal? Like, here, let's get married, and grasp the core meaning.
Understand the words.
Right. And can they project the basic content of that agreement forward? Meaning, do they understand the immediate primary consequence? Like, if I say yes, the law will consider us married. It's often a fairly basic threshold.
So, how would a robot demonstrate that?
Well, this clearly requires some pretty sophisticated information processing. Just extracting the proposal itself involves natural language processing, or NLP. The AI field focused on computers understanding human language.
Which we know from chatbots isn't perfect.
Far from it. The article acknowledges NLP is still imperfect, but it suggests you could mitigate errors, maybe by requiring the robot to confirm its understanding. Do you understand that agreeing means we will be legally married? Or maybe even using written proposals. Extracting the core meaning could involve identifying keywords, understanding related terms through lexical affinity, and maybe even using things like semantic networks or scentic computing to grasp the implications or consequences.
But doesn't this immediately run into that huge philosophical problem? Does processing language actually mean true understanding? This sounds like Searle's Chinese room argument.
It absolutely is, and the article brings it up directly. John Searle's famous thought experiment from the 80s, right? He imagined this person locked in a room who doesn't know Chinese but has a rule book in English telling them exactly how to manipulate Chinese symbols based on their shape. Questions in Chinese come in, they follow the rules, and perfectly valid answers in Chinese go out.
But the person inside has no clue what they're saying.
Exactly. Sturl argued that even though the system looks like it understands Chinese from the outside, the person inside has zero actual understanding or intentionality. He argued true understanding requires consciousness, which he believed computers lack.
So, how do the standard replies to Searle, which the article mentions, fit into this idea of robot consent?
Well, two main replies are relevant. First is the system reply. Maybe the person alone doesn't understand, but the entire system, the person, the rules, the symbols, the room, collectively understands Chinese. Applied to AI, maybe no single algorithm understands, but the whole integrated system does.
Okay.
The second, maybe even more relevant for us, is the robot reply. This suggests that if you take that Chinese room system and put it inside a robot body, allowing it to actually interact with the physical world, see things, touch things, move around, then it would gain genuine understanding. It could connect the symbols to actual objects and experiences in the world. This ties directly back to the embodied AI we were just discussing. It needs that grounding in reality.
Right, connecting symbols to reference. But legally, does this whole deep philosophical debate about true consciousness versus symbol manipulation actually matter for determining if consent is valid?
This is where the article makes a potentially surprising argument. It suggests that for the law, maybe it doesn't matter as much as we'd intuitively think. Law often takes a very pragmatic of consciousness. The article even posits, could passing a really sophisticated version of the Turing test, where a robot's behavior is indistinguishable from a human's, be enough for the law in this context?
Wow.
And it argues that case law might already be pointing in this direction. Courts are, in some situations, increasingly treating the actions of complex autonomous machines as equivalent to human mental states or intentions for legal purposes.
Are there examples in the source?
Yeah, it mentions a couple. United States v. Flowerday back in the 70s, involving automated phone call processing. The court essentially treated the machine's actions functionally like those of a human operator. Another is Thrifty Tell, Inc. v. Bezenek in the 90s, where a computer network's automated response to hacking was considered legally analogous to an agent's actions for establishing reliance in a fraud case. These suggest a precedent for focusing on what the machine does functionally, not its subjective state.
And they bring in this idea of AI hermeneutic theory. What's that about?
Yes, that's based on work by Zhu and Chopra. They propose a way to attribute things like intentionality, knowledge, or belief to AI systems based purely on a functional analysis. Their theory suggests if an AI shows certain characteristics like it acts autonomously, its internal workings are complex and opaque, a black box, its behavior is relatable or understandable to us, it was designed with some intention, and it can act on information, then, for legal purposes, we might just attribute knowledge or intent to it.
Even if we don't know what's really going on inside.
Right. It's about interpreting the AI's actions and outputs as if they were expressions of intent based on its observable capabilities and how it interacts with the world. It's a functional interpretation for legal ends.
Okay, so that's understanding, potentially handled functionally. What about the second criterion, retention?
This one's a bit more straightforward, legally and technically. Legally, retention just means having the memory capacity to hold on to the relevant information like the marriage proposal and understanding its consequences long enough to make the decision.
And robots are good at memory.
Extremely good. Computer systems are built for storing and accessing huge amounts of data instantly and ideally retaining it indefinitely. While sure, memory faults or system crashes can happen, those are generally manageable with things like backups and redundancy. In many ways, a robot's recall could be far superior to a human's.
Okay, now the third criterion, formulation of decision. This sounds like it gets closer to what we think of as uniquely human. The law mentions weighing options, considering goals, values, maybe even emotions, social reactions, having idiosyncratic values.
This is definitely where the challenge for AI seems greatest, but again, the article argues it might not be an insurmountable barrier from a purely functional legal perspective. Robots are already very capable of what's called instrumental reasoning, meaning performing cost-benefit analysis, evaluating different paths to achieve a goal, selecting the most efficient or optimal one. AI planning systems like the strip system mentioned in the source, or techniques like dynamic programming, are specifically designed to figure out sequences of actions to reach objectives. They often do this with a level of computational rigor far beyond what humans do consciously.
But what about the values part? The legal definition mentions considering personal values, identity. Can a robot do that? Are its values just programming?
That hits the nail on the head. It's the core philosophical question here, and the article acknowledges it. Can an AI truly have internal values? Or is it just executing its programming or optimizing a learned reward function? They mention ongoing research trying to build more complex AI minds with things like learned values, richer memory systems, simulations of emotional responses, and logical reasoning, citing researchers like Thilmany and Franklin.
Could something like a robot's core programming, like a survival imperative, or maybe programmed ethical guidelines, serve as analogous to internal values for legal purposes?
The article suggests maybe. Could those programmed imperatives or learned societal norms function like internal values when the robot makes decisions? It even suggests that coercion, for a robot could perhaps be defined functionally as a situation where some external pressure creates a high cost that conflicts directly with these core programmed imperatives or values.
How does this compare to the standard for humans getting married? Do we need a perfect value system?
Not at all. The article makes the point that the law doesn't require humans to have some deeply coherent philosophical framework to get married. The legal bar is primarily about having sufficient mental capacity to understand the act and consent to it. The difficulty is, how do you define sufficient mental capacity for an AI? That's the open question.
And the last concept tied into consent was communication.
Yes, simply the ability to express the decision, either verbally or non-verbally. From a robot's viewpoint, the article frames this largely as a technical issue. Does it have the necessary interface speakers for voice, a screen for text, maybe actuators for gestures to convey its agreement or intention?
So, putting these functional takes on understanding, retention, decision formulation, and communication together with the legal idea of competence, what's the bottom line from the legal source on whether robotic marriage is theoretically possible?
Their conclusion is pretty striking. They essentially ask, why not robotic marriage? Their argument, weaving together these legal principles, is that the law often leans towards this functional or intentional approach when it needs to predict outcomes or attribute intent.
Focus on the function, not the feeling.
Right. And given that case law seems increasingly willing to treat the actions of complex autonomous machines as equivalent to human actions for determining legal mental states, well, then a robotic entity, if it were granted legal personhood and if it were deemed capable of entering contract.
Even with all these striking parallels between the tech capabilities and the functional legal criteria, there's still a pretty big gap, isn't there? The technical source is all about performance metrics, success rates, path lengths. It never talks about subjective experience, consciousness, feelings, true values.
That's the fundamental divide, and both sources really acknowledge it, either
Yeah.
directly or indirectly. The tech source is purely focused on building functional capacity. Can the robot do the thing? Can it see, move, map, learn, describe effectively? It's not asking if the robot feels anything while doing it.
Well, the legal source brings up Searle and the philosophical problem.
Right. The legal source grapples with that philosophical debate, true understanding versus just simulating understanding. But, and this is crucial, the legal source suggests the law might ultimately sidestep needing to solve the consciousness problem. It might adopt a functionalist standard. If the entity acts in a way that demonstrates understanding, decision making, and communication, and if its internal workings are complex enough, that operational opacity idea, then the law might just attribute intent or capacity based on that observable function.
Regardless of what's actually going on inside, subjectively.
That's the provocative possibility raised by the legal analysis. It shows how the law, built for humans, has developed tools like corporate personhood, like functional definitions of consent that could theoretically be applied to non-biological entities based on what they do, effectively bypass lead AI, detailed in that first source, is genuinely accelerating. These aren't just theoretical lab experiments locked away anymore. Robots are getting more sophisticated, more capable, and more integrated into our world, warehouses, hospitals, maybe soon our homes. Real world deployment is happening now.
And so the legal questions, like those in the second source, are moving from academic theory to potentially real world issues we need to grapple with.
Exactly. As robots become capable of more complex interactions, maybe even interactions that start to feel like relationships, think elder care companions, household assistants, the legal questions become urgent. Who's liable when an autonomous car crashes? Can a robot own the data it collects? Can it inherit property? And yes, the extreme example the legal article uses, could it have the capacity to enter contracts, maybe even marriage?
That marriage question really crystallizes the issue.
It serves as a powerful lens, doesn't it? It forces us to confront these fundamental questions about what actually defines a person in the eyes of the law, what constitutes always reserved exclusively for humans. The technology is forcing the conversation.
It really challenges our sort of default human centric view of who gets rights and who counts as a person.
It absolutely does. It makes us question whether our definition should be based solely on biology and subjective experience, or whether function, capability, and role within society should also play a part. The sources together show technology is actively pushing on those boundaries.
Okay, so we've taken quite a journey here in this deep dive. We went from the really intricate technical details of how engineers are building intelligent, interactive robots that can see, move, and even talk about the physical world.
All the way to the history of legal personhood, looking at things like corporations and dissecting the functional tests the law uses for something as deeply human as consent to marriage.
And the connection we found is how those cutting edge technical capabilities being built today seem to align, maybe surprisingly closely, with those functional legal criteria for assessing capacity and consent, even while the huge philosophical questions about consciousness are still completely unresolved.
Right. The combined picture suggests that this idea of human robot legal marriage, while sounding outlandish, just pure fantasy. It's a theoretical possibility grounded in the very real, very rapid advancements in embodied AI when viewed through the lens of existing legal principles that could be interpreted functionally to include non humans.
It's a future that's actively being built and competence to enter into a marriage contract. If it demonstrably shows understanding, decision making, retention, and communication in a way the law says is sufficient, is there any overriding ethical or moral reason, separate from the purely legal one, why it absolutely shouldn't be allowed to marry? And if you think there is such a reason, how would you define that barrier? How could we articulate it in a way that isn't just based on biology, but on some deeper, more principled distinction?
That's a question that definitely forces us to look inward at our own definitions and values, just as much as it forces us to look at the technology itself.
Thanks for joining us for this deep dive.
Thank you.
All right, so that's it. This has been Military Industrial Museum. Check out my channel. Might even want to subscribe and support me that way, but got some good music, got some little anime videos, a lot of AI stuff. All right, peace out.